Okay, welcome everybody. Second presentation in this channel is Senior Design Team from Electrical Engineering. This team designed a fitness flight simulator as their senior project, and their members were Jacob Brothers, Ronald Debo, Robert Goodrich, Connor Hunt, and Jacob Young. And RG, you're driving the slides, right? Okay, thanks guys.
All right, thank you, Dr. Rumbaugh. Like you said, our project was a fitness flight simulator, abbreviated FFS, for our senior electrical engineering senior project. I'm the team leader, Connor Hunt, and the rest of our team. So Jacob Brothers was assistant team lead, RJ Goodrich was our secretary, RJ Debo was our purchasing agent, and Jacob Young was our customer liaison. As well, we'd like to thank Dr. Rumbaugh who is our advisor, Mr. Gillette, who is the electrical engineering technician, and Mr. Peisch, who assisted a lot with mechanical as a mechanical technician. So you might be wondering, what is a fitness flight simulator? Well, we figured the easiest way would just be to show you a video of it working, just to start right out. So as you can see here, we have someone actually operating the flight simulator. So they're playing the game by operating what you would normally see in an aircraft. They have a flight yoke, they have throttle, and they have rudders, and it's also providing mechanical resistance, so it's acting as a workout. So you can see he's playing a game. In this case, it's a dogfight simulator. So that leads right on. So the main game that we were working with is called Crimson Skies. This was requested to us by our customer. This is an older game, which is nice because it worked on our laptops, though our flight simulator is also designed so that can work with any standard flight simulator game. It acts as a generic gamepad to any computer. So as a little background, here's the different sections for our project. We'll show you this block diagram throughout the project just to kind of reorient you with what we're talking about. We'll start with the frame and the physical components, how everything is connected together. Then we'll go into controls and how everything electronically is controlled and connected together. Then we'll go on to exercise monitoring and feedback, and finish off with the electrical systems and how everything electrically is powered. So some goals that we set up for ourselves at the beginning of the project was to ensure that there was realistic gameplay while it's still a lot of fun. So you want to have fun while still enjoying some realism while using this. We also wanted it to interface with a PC just as a generic gamepad, so you could play a game. And we wanted to provide a functional workout. It's designed to provide a cardio workout. So over time, you get a workout. We wanted it to provide health monitoring capabilities, so you could see how good of a workout you were getting, and to accommodate people of different sizes and heights. And it should be movable by 2 adults fairly comfortably, and it should provide a spot for a TV to be mounted so you could actually see what the game was. Next up, Jacob Young will be talking about the frame.
Hi, everyone. I'm Jacob Young, as Connor stated, and I'm going to be talking to you about the frame, which, as you can see here, consists of the pedals, the throttle, the chair harness, yoke, cart, and yoke. So first, I'm going to give you an overview of the product. So this kind of lays out where everything is placed. As you can see in the top right, we have a TV bracket, which was simply we went out and bought an external bracket that would allow us to meet the specification to be able to handle lots of different TVs and or monitors that would be used with a PC. And then you can see where the yoke, cart, pedals, throttle, and yoke are placed. So now I'm going to be going into a little more detail about the yoke. So the yoke, as you can see, we have it 3D modeled. We decided to do that because that made it much easier for the machine shop when machining our parts to have an idea of what the total product of all of the individual pieces they were machining would come in to be. And then since it was being made out of steel and welded, it had to be quite accurate, as well as the box there, as you can see, we designed it in 3D space so that we could try and have multiple different alterations of it, and that way we could modify it as we needed to go. And then the physical representation came out to be this. So as you can see, the black tubular bars are made out of steel. They've been welded together. You can see the weld markings there. And then we had 10 push buttons in our box. We had 4 for the D-pad, 2 for a start and select, and then 4 for the ABXY general scheme that comes on a normal game controller. And then in the top left of the image and the top right of the image, you can see that we have 2 red push buttons. These are tied through software to the A and B buttons for ease of use to allow more realistic. So in the game setup in Crimson Skies, it would be machine guns on the left-hand trigger and it would be the missiles on the right-hand trigger. So next I'm going to talk to you about the yoke cart. The yoke cart is very specific. It is where the yoke attaches to the rest of the frame in such a way that it provides us with a measurable motion in both 2 axes. So it can also be resisted as well. So in the you can see on the cart that we have 2 rotational bearings. These bearings allow the rotational motion of the yoke, and we have a track for linear motion. So that allows you to pull the yoke and push the yoke away from you. We have 2 set screws in the bearings that allow you to go in and lock the yoke bar into place in such a way that when you pull it, you pull the yoke and you pull the yoke cart with it, as well as when you rotate it, as you can see we have a spring there, it allows you to supply a rotational force on it. So in the next image, I'm going to be talking to you about the pulley system that we have in place to allow for a linear resistance on the cart. So as you can see, we have 2 pulleys below the yoke track and 2 pulleys above. This allows you to have a resistive motion on the bands down below that will supply it so that you will have resistance when you push it and resistance when you pull it, as well as there are 2 knots inside the yoke cart that allow you to pull it and push it and still receive the force from the 2 springs. And now I'm going to hand it off to RG.
Thank you, Jacob. So what I ended up starting with here was I will start by talking about the pedals. So when we were first getting into this, we realized that we wanted to have a relatively simple design that was cost effective, that provided a tough workout over time. And the reason for this is because we're electrical engineers and we want to worry about more about the controls and how we're actually going to emulate all this different information into the game. So while this model is on the right, the physical realization then appears there. You can see the springs outlined in yellow, and where the springs latch on is outlined in red. This allowed us to then basically have that simple and cost-effective design we wanted, and it provided a max weight of 20 pounds, and we'll talk about the implications of that a little bit later. And the final part of the frame is the seat. Now, if we think about our goals, first we wanted horizontal and vertical adjustability because we wanted to accommodate a wider range of heights. But then we also need to consider the safety of our user. Because of this, we needed the support to be very strong because the user is going to have all of their weight seated there in addition to all of the forces that are going to be acting. So the physical realization then pops up and we see that this is a very strong design, but it doesn't really have any of that adjustability that we wanted. And there's a very good reason for this. And it's because that, again, we wanted to talk about the electrical systems and we wanted to worry about that. So we just needed something that was cost effective, would support the user strongly, and was kind of a placeholder for the user to sit while using the system. And now I'll be passing it back on to Connor to talk about the controls.
Thanks, RG. So the controls are the brains of the system, what actually connects it all. So controller emulation, all the sensors for all of the axes, which we use potentiometers, and the buttons on the actual yoke. So our first axis, our first axis is the pitch. So on an actual airplane, the pitch of the airplane is when you move the nose directly up or directly down. This is controlled by pushing the yoke directly into the machine or pulling directly out of the machine. Pushing into the machine will cause your nose to go down, pulling out will cause it to go up. The operation is then transferred from the yoke back to the yoke cart. As you can see here, this is the system underneath the yoke cart, which is actually measuring where it's at any given moment. So go back, sorry. So yeah, we have some 3D printed parts here. So we have a 3D printed gear rail, which is stationary, and a rotational gear that rides along it as the cart is pushed back and forth. And its position is measured with a potentiometer, as you can see there. The voltage across the wiper is measured at any given point to be able to give you the position of the cart. Our next axis is the roll. So on an airplane, the roll is when the wings move left or right, rolling, if you will. And then this is controlled by rotating the yoke left or right, similar to a steering wheel. This is then rotates the axle all the way back. As you can see on the yoke cart here, this is measured again with a potentiometer. We have two gears, once again 3D printed, attached to a potentiometer where it's measured in much the same way by measuring the voltage on the wiper. The third axis is of course yaw, which is moving the nose directly left or right by changing the rudder. This is controlled with the foot pedals like you would have on an actual airplane. So in our system, you can put your feet anywhere along the rudders, and as you push it left or right, it'll rotate the plane accordingly. This is measured along the top middle of the system. Once again, a potentiometer is mounted, and once again, you measure the wiper voltage. And as you rotate the pedals, the potentiometer rotates along with it. Then our last axis that we had to measure was a little bit different, was the throttle. The throttle experiences no resistance, just like mechanical resistance like the other ones. This was just so you can control the speed of the aircraft. So this you generally don't change as often, and it's just a quick change and it stays there. So this is kind of off the side of the user. So we decided it wasn't worth it to put any resistance on it. So it has it's entirely 3D printed, designed by us and then 3D printed, and contains once again a potentiometer measuring the voltage across the wiper. This one's also a little unique because it is off in a different location on the machine, and as such we decided to transmit the data via Bluetooth to the main control panel. This is the only axis or control that uses Bluetooth. We'll get into a little bit later about why that was good and bad. Next up, we have Jacob Brothers talking about exercise monitoring and feedback.
Thanks, Connor. Hey everyone, I'm Jacob Brothers, and I'll be talking about the systems that our team used to allow the flight simulator to monitor a user's workout. As you can see here, we have a few key elements in the form of a game demo. It's basically just a game that we created that allows the simulator to give us more control over the entire simulation than Crimson Skies, the original game, had. The game the simulator also features an LCD screen that enables us to give the user direct feedback on a few metrics as far as their workout goes. The system also features a heart rate sensor, which is basically the foundation of the feedback system. It's pretty much what everything else is built off of. So on the next slide, starting from the ground up for our metric systems here, we have the pulse monitor, which you can see it's hooked up to a spot inside of the yoke handle. As you can see here, we modeled the handle in CAD prior to building it so that we could find a good spot for the sensor to go. Next, we have an output waveform that is being generated by the pulse monitor. You can see it's a pretty standard pulse waveform. The peaks are just the main portion of each pulse that is being produced by the user. The system basically takes these peaks and calculates a heart rate based on this over time. So the heart rate itself is actually fed back to the user via the LCD screen, as well as used to approximate a calories burned value that we also show the user via the LCD screen. On the next slide, we have the LCD setup. This basically displays information using 3 different slides. On the first slide that you see here, the LCD is displaying the beats per minute or the heart rate of the user. On the right, you can see the LCD actually features a touchscreen, which enables the user to cycle through the different slides depending on the information that they want. So on the second slide, you'll actually see we have the calories burned figure. So this is basically just a approximation based on a formula that was given to us by the exercise science department. It uses the heart rate of the user combined with a few various weight metrics that are just standard, not built into the simulator, and it approximates calories burned based on the duration of the workout. On the third slide, we have the wave number displayed. That's a feature in our game. I'll talk about it in a little bit, but essentially the wave number is just a virtue of how difficult the game has become. On the next slide, here you see our game. It's the last portion of our feedback system. It's basically the proof of concept for the interface between the game systems itself and the hardware. So it basically demonstrates the fact that we can implement a few features to monitor metrics and basically control the simulator via a game. The primary piece of information that's important here is the score, which is being calculated based on the user's average heart rate over the course of the game. But on the next slide here, we have a features review, basically. So a little bit about the controller emulation, as Connor was talking about. We have potentiometers for each axis. They basically individually allow for controls of the user to be interpreted by the system as game input. So all of the user's movements are somehow being interpreted as game movement. And then on the other side, we have the feedback systems, which basically allow for it's essentially the heart rate system, the LCD, and the game, which basically come together to provide the user with feedback on the intensity of the workout that they're experiencing. And next, I'll hand it off to my partner, Debo, and he'll talk about the electrical system.
Hello, everyone. My name is RJ Debo. I will be continuing a description of our design by talking about the power distribution and control wiring of the system, as well as our validation methods and results. To power the FFS, we utilize two different methods. Our first method was DC power. With batteries, we were able to power our throttle Bluetooth connection. Our second method was AC power using a power strip. Plugged into the power strip were a TV and 3 9-volt adapters. 2 adapters were used for the Arduino Due and Arduino Uno that were used for controller emulation. The final adapter was used for another Arduino Uno, which powered our LCD screen. Our first validation method was ensuring that the FFS was easily movable by 2 adults. This meant having it weigh under 300 pounds. We chose 300 pounds because the average adult can easily deadlift 150 pounds, and 2 times 150 is 300. As you can see, we easily accomplished this goal, as the FFS weighed in at roughly 155 pounds. Next were our tests on our resistance systems. Through conversations with Dr. Buxton of the Exercise Science Department and our workout labs, which we conducted in the fall, we were able to determine our target weights for each workout. Our first workout was bench and row. RG attached the force gauge to the base of the yoke, and he pulled back as far as he possibly could. When the yoke cart is pulled back as far as allowed, that is whenever we took our maximum force reading. Our target weight was 75 pounds. However, we only obtained 45 pounds. Luckily, this worked out better than 75 pounds. 45 pounds allowed for a workout that the player could complete consistently. 75 pounds would have been far too difficult for any player. Next, we tested the rotational force. For this, we attached the force gauge to a bar that the spring was also attached to. To get our maximum force reading, we then turned the yoke to 90 degrees. For this workout, our target weight was 50 pounds, and we obtained 50 pounds. Dr. Buxton's recommendation, in conjunction with our labs in the fall, provided for a perfect workout weight. Our final resistance test was the leg press. For this test, RG attached the force gauge to the same point of contact as one of the springs that was attached to the pedal bar. He then pulled on the force gauge until the pedal bar was turned as far as possible. Our target weight was 100 pounds, but we only obtained 20 pounds. The main reason for this, as RG mentioned earlier, was that we wanted to just get something on there so we could begin working on controller emulation. Finally, our last validation method was taking a survey of people who played the game. We were able to obtain results from 10 participants as we set up the FFS in Hoyt Atrium. It is still there for those who are interested in playing, as we will continue to take surveys to get a wider range of results. We decided to take these surveys for multiple reasons. First, we wanted to figure out if the workout overshadowed the fun level. We then wanted to determine if the game still felt real. And finally, we needed to make sure that it felt comfortable while the player was playing. Our results were based on a 1 to 5 scale. As we can see, the fun level, rated at 4, remained high, although the workout was moderately difficult. For the most part, participants felt as though the game still felt real, and finally, the comfort level, 4, remained high while volunteers played over a 5-minute period. I will now give it back to RG, so we'll talk about our goals to date.
Thank you, Debo. Okay, so what you see right here is actually our first set of goals that we showed you at the beginning, just as a kind of a refresher. So our first major goal was ensuring realistic gameplay while maintaining enjoyability. As we just showed from the survey, people were actually having quite a good bit of fun while having realistic gameplay. So this means that we actually reached this goal very well. Our second goal of interfacing with the PC as a gamepad is also succeeded because we actually can turn all the different parts of the FFS and all of those different motions will translate directly into the game so that you are actually flying the aircraft, not just moving around a controller. Then we wanted to provide a functional workout. As Debo just stated, these are a little bit different because we had these sort of targets that we wanted to go towards, but there wasn't necessarily any sort of basis for why we were going there other than suggestions from a workout perspective and what we saw in the fall. So we feel pretty comfortable about what we've done so far, and people have reported actually having a moderately difficult workout. So we feel that this has also been successful. We wanted to provide health monitoring capability, which we have succeeded by showing both the heart rate and the calories burned on the LCD for the user to see. Comfortably accommodating users of heights 4'6" to 6'6". This wasn't met entirely, and we talked a little bit about this earlier because the chair, we wanted it to be adjustable, but it just cost a little bit too much for us, especially because we wanted to go for electrical systems. However, during the survey, the heights listed of the individuals range from 5'6" to 6'4", so we can at least say that those users were comfortably accommodated while playing the fitness flight simulator. Then we have the entire system being movable by 2 adults. The validation method you saw saying that showing the FFS weighing less than 300 pounds proves that this goal succeeded. And then the overview we showed at the beginning of this presentation showed the TV bracket, which supports a wide range of TVs and supports up to 65 pounds, meaning that this goal was also completed. Some things we actually learned from this project, though. We'll start off with the technical. The frame, wider legs would have improved the stability of the FFS. It's not dangerous by any stretch of the imagination, but it could be improved better, especially if the design of the FFS is changed in the future. The next two kind of go together. From an ambitious resistant goals and unforeseen torque concerns, the yoke cart actually has quite a short base for the amount of torque that's formed right there. So by redesigning the yoke cart or widening the yoke cart base, we could actually fix that issue. And we also, as stated just previously with the goals, the linear force was a little bit too much. We wanted to get a little bit too much with our leg press as well. So maybe revising those would be better for the FFS in the long term. Two of them, 2 small yoke pipe and the wiring benefit of 80/20 goes tied directly together when considering the wiring of the FFS. A larger pipe would create a lot more room, especially considering the torque arm that was through the pipe. And the channels of the 80/20, while we don't expect 80/20 to be used for the FFS in the actual future and about how it's going to be actually constructed, we think that channels in whatever material they use would be useful to give it a much cleaner look from a wiring perspective. And pot resolution concerns was our final thing we kind of learned. We could switch to encoders to give a greater deal of accuracy in the code, but it still operates effectively as a gamepad. And then on a more general perspective, we've realized three major things. The value of interdisciplinary experience cannot be understated. We have realized throughout our time here that we have had to do both mechanical systems and electrical systems on this project. In order to do that, we talked with the machine shop, and we actually understood the needs of them just as much as the needs of what our team needed. Some of the ideas we have just aren't feasible, and we wouldn't necessarily be expected to do that, but it's important that we actually realize this for our future value in our careers. And then the usefulness of modeling and 3D printing. Without this sort of modeling and 3D printing, we were sort of at the mercy of the machine shop, and they get very busy. They've done a great job this semester of distributing out work to all the teams, but this allowed us to actually take matters into our own hands. In addition, the modeling allows each team member to actually put their idea as something that everyone can see. That way you're not getting misinterpretations of what you're expected, and you're not going to waste any time or materials on ineffective designs. And then finally, the importance of a team with individuals of different strengths. All of the people on this team have different backgrounds, whether we have people with game design backgrounds, people with communications backgrounds, some more people with exercise science experience. All these different things played a crucial role. And we've learned that if you have people with all the same background, it's not going to work out very well, and we're going to definitely remember this for the future. And then suggestions for the future that we think would really take the FFS to a great level. First off the chair. We did actually come up with a second iteration, and as previously discussed, we didn't have enough money to do that. However, implementing this new chair design allowed for both vertical and horizontal adjustment capability would be very good and really kind of bring the whole look of the fitness flight simulator together, a much cleaner look, if you will. And second, we have variable resistance. As of right now, as you saw, we only have bands and springs on this thing, meaning that we can't really change it to match a person's needs any better than the next. Actually making this variable would be very good because it would appeal to a wider range of audiences. Third, we have Bluetooth. As we discussed, the throttle was communicated wirelessly over Bluetooth, but if we actually put this on the yoke, we would completely eliminate the wiring problem we were talking about earlier about what we learned. This means it would allow for a much cleaner look and a simpler design from a wiring standpoint. From a gameplay perspective, we could really kind of go anywhere with this. We could do a much more immersive experience. We could do a lot more feedback. The ones that really stand out is the fact that by showing this game and this proof of concept, we can kind of give feedback for any sort of game. We can create anything we want, what our customers decide to give us as feedback. We can implement that in later iterations. And that's really going to bring in more people, and it's going to really make our current customers happy. And then finally, we have the heart rate monitoring. Well, it doesn't work out exactly as intended just because sometimes, based off that design, when you grip it a little bit too hard, the method of taking the heartbeat doesn't quite work. If we improve the integration of that pulse monitor, it would be a lot more consistent in its readings and it would provide a lot greater feedback to the user. All of these things, if iterated, would really bring the FFS to the next level, and we feel that it would be very successful in the marketplace. And finally, we want to give a couple thank yous out. First, our sponsor, Mr. Hensel. Without him, this project wouldn't have been possible, and his expertise on these matters was invaluable. Second, Andrew Thompson and Zach Dunkley gave a lot of mechanical engineering experience in a variety of capacities, and without them, this project also wouldn't have been possible. And then finally, the GCC machine shop for their assistance throughout the year was absolutely invaluable. Without their work, we could not have implemented the FFS to the capabilities that we did. And a big thank you for that. Any questions?
Thanks, guys. Let me suggest that the team members all go ahead and turn on their webcams now. And audience, if you have questions for these guys, go ahead. I can break the ice here. Guys, would you talk a little bit more about what kind of electronics you use to actually get the translate the movements of the cart and the yoke and stuff into signals that were passed on to the PC?
Yeah, I can talk about that a little bit. So we actually have a diagram that kind of describes this a little bit, but it was primarily done, like I said, through potentiometers to measure it through to voltage. And then we also used a series of Arduinos throughout the system. So if I'm pulling it up here, we have one of these extra slides. I saw it. All right, well, yeah, there it's see. So we have 4 Arduinos and a couple of feathers that are connected through various connections. We have Bluetooth, serial, I2C, all of which are sent on to PC via USB serial from our master Arduino Due.
Can you say something about why you chose to use 4 Arduinos and why that number, and I guess why you chose Arduinos in the first place? Some reasons for those choices.
Yeah, I can answer a little bit about that at least. So Arduino was pretty much a choice because we knew that it would interface well with the game engine that we were making, Unity. So basically, they support a pretty native serial connection. The number of Arduinos was largely in part because Uno was the most available one, and they support a single serial connection, so we needed to use quite a few to get everything done, as well as just spreading out everything across the actual physical prototype. We had to. It was a little bit hard to centralize everything, but the main reason behind Arduino itself versus something like Raspberry Pi was just because we were a lot more familiar with Arduino, and we didn't want to throw in another variable as far as like learning a whole new architecture, basically.
I'd also like to add, like some of the Arduinos were for specific parts. So for the LCD, for example, that was a shield that went directly on top of an Arduino Uno, so it was basically required for that. We needed our library that supported acting as a joystick only supported a few different kinds of Arduinos, so that limited our choices there. And like you said, we just needed a lot of ports for all these different buttons and inputs.
Are there audience questions for the team? Gentlemen, while we've got you here, would you care to speculate a little bit about the business prospects for this flight simulator? This whole study was kind of done as an entrepreneurial experiment. What do you think it would take to put this out on the market, and do you think it would be successful?
I can go first. I personally think that the incorporation between an exercise machine and a simulator, whether it be a flight simulator, a driving simulator, whatever it happens to be, I think it's really cool because the few times that I've sat down and played it for a decent amount of time, I don't really notice that it's much of a workout, which is kind of the whole point. You know, you can sit down and play for a half hour and not realize that you just worked out for a half hour. If it was, you know, taken on by some, you know, professional corporation and really fleshed out, I think it could be a phenomenal product, assuming they got the pricing right. I don't know how many people would be willing to pay, you know, tens of thousands of dollars or anything like that. But if they could keep the price reasonable, I think that a pretty decent amount of people would be interested in purchasing something like that, especially because, working out easy is pretty desirable to a lot of people. Not a whole lot of people, want to sign on to a really hard workout. They want to do something that's easy and fun while they get healthy. And I think that's kind of what this is perfect for.
Also like to add on that, especially in the world we're in today at the moment, where especially with COVID, I don't know how much longer that's going to last necessarily, but it has shown that there is the possibility that people are going to be kept in their homes for an kind of indefinite amount of time. And people really want to have fun, but they also want to be able to stay in shape, and you don't have the opportunity to go to the gym or go run at your favorite track the way that you would have in a pre-COVID era. So this kind of fits that niche very well.
And I just want to add one more thing. Through the surveys and I myself playing it, the game itself was very fun. I played it, I don't know, probably for a total of 20 minutes or so, and I had a lot of fun playing it. And like Jacob was saying before, you barely even notice that you're getting a workout. And the fact that there's opportunities still to improve upon the design, like RG was saying before, variable resistance, and of course, like RG was saying, the market's there for the taking, so I think it's a very good opportunity.
Just a point of clarity as well. After having worked out for 10 or 15 minutes, I definitely feel like it's a pretty good workout. I just, when you're actually like in the intensity of the game, trying to fly around and stuff like that, it just kind of goes by the wayside how sore you are or whatever. But afterwards, not with the legs, obviously, as we had kind of mentioned, those are somewhat placeholders, but the benching and rowing and the twisting motions, those get difficult after a while, for sure.
Thanks, guys. I think we have time for one more question if there's anybody who'd like to ask these guys. Okay, well, if there's no further questions, then gentlemen, great job. Thanks for telling us about your work. It's impressive, and it's a nice interdisciplinary project that a lot of people are going to enjoy playing as they walk through Hoyt Atrium over the next couple weeks. We'll pick up our next presentation at 7:30 with underwater time of flight camera. So if that team could go ahead and start to put their slides up, that'd be great. If you were planning on going to another channel for a 7:30 meeting, they should all be synchronized, so you should be free to do that. That should work out smoothly for you. All right, thanks again to the Fitness Flight Simulator team.